Good morning, ladies and gentlemen. Let me state that we are delighted to see you here, that you came to our seminar, Colloquium. And I will start with saying that the next Colloquium will be held on 18th of December, not on 4th, but on 18th of December. Excuse me for misleading information, the mailing. Passing to today's colloquium, we'll have a pleasure to listen to two speakers. Both of them are workers of our faculty, our university. The first speaker is Professor Katarzyna Krajewska, who works in the Institute of Theoretical Physics, and she's well known for a series of lectures of quantum mechanics at our faculty that are highly appreciated by students. But in fact, she works in the subject of physics of high or of strong and ultra-strong fields. The second speaker of today's colloquium is Professor Piotr Wasylczyk, who works in Institute of Experimental Physics. He deals with optics, and also it is not well-known fact that he also works at University College of London. And in London he works on diseases of an eye, methods of curing such diseases. So optics, but let's say applied and in medical aspect. And today we are going to listen to the lectures about Nobel Prize in Physics that was awarded for attosecond pulses. And if you check the list of Nobel Prizes over the 5 recent years, you will see that 3 Nobel Prizes were awarded for physics related to optics in general sense, because 5 years ago there was a Nobel Prize for femtoseconds, a year ago for quantum optics, and this year again for laser physics, attoseconds. So it looks that optics is a good subject to get a Nobel Prize. I hope that you anyway listened to what I was saying. With that, I will finish and I will give floor to Piotr Wasylczyk.
I just realized that this can be considered an encouragement to sit at the bottom, but it's not. When Feynman said this in December 1959, he referred to small scales, and this is considered, this lecture of his at Caltech is considered to be a vision of nanotechnology. And that's indeed one way to do science, is to try to explore extremes of scales. It's usually a very expensive way of doing science, and you can explore time scales and length scales. So you may want to build the biggest or the smallest or the fastest. And somehow these scales are related. We live somewhere here, and then if you consider planets and universe, they are bigger and they live on a longer time scales. But today we will go in the opposite direction towards molecules and atoms, and well, nuclei is still the future. But people were always interested in looking at this extreme, so to look at time scales shorter and shorter, and there was Nobel Prize in the 60s, which is, I think, quite interesting. That was 7 years after the first demonstration of a laser, and still you could get a Nobel Prize for using flash lamps, because these gentlemen were using flash lamps to study fast chemical reactions. And well, their time scale was on the order of microseconds, and I will refer to that a bit later. Let's start with some basics. So basics are lasers, and as we teach students to build a laser, you need a medium. Then this medium must be pumped by some energy source to excite atoms or molecules. And then we build a resonator around the medium, and that's basically it. We can, if we pump strongly enough, then we can expect to have laser output. What if we look at the frequency domain at this output? So assuming everything is perfect, in the sense perfectly stable, mechanically thermalized, we will see an envelope of this medium amplification. There is a certain range of frequencies where we can expect amplification. And under this envelope, we will see equally spaced modes of the resonator. And I often tell students that the distance between these modes is one of very few formula worth memorizing in optics. This is the inverse of the cavity round trip. Interestingly enough, if this is the length of the cavity, and you consider this is the speed of light, well, either in vacuum or in this medium, then this is the inverse of the cavity round trip. So a laser generally generates many modes. There are, of course, single mode laser when this spectrum is very narrow, so maybe we can excite only one longitudinal mode. We can play some tricks, but in the pulsed laser technology, generally, we want many modes, as many as possible, several thousands maybe. In this laser, all these modes are generated independently. They know nothing about their colleagues. So this mode knows nothing about the other ones. To get pulses, what we need to add two elements to our cavity. So first of all, we need to add some nonlinearity. There are different tricks. It can be a saturable absorber, like graphene, or it can be some clever tricks playing with this, with nonlinear effects in this amplifying medium. Plus, we need to know some dispersion control, which I'll schematically draw here as a pair of prisms. And now we are ready to generate pulses. And now, if this nonlinearity is working, if it works, these modes start to see each other, and they can be synchronized. Their phases are not independent anymore, but we can phase lock them, and this is usually called mode locking. And this is the principle of all laser generating femtosecond pulses. With this technology, we can get, let's say, down to 5 femtosecond with effort, let's say 100 femtoseconds easily, very low energy on the order of pico or nanojoules, typically in the near infrared, 800 or 1 micron central wavelength. So the message of this is short pulses. For short pulses, we need many modes, and we need to know the phase relation. We must be able to establish phase relations between them and control this and also measure this. And well, in my story, this is the Nobel Prize of Ahmed Zewail from 1999, although he's a chemist, but he was using short pulses, femtosecond light pulses, to study chemical reaction, because as you might have seen on my scale chart, the oscillations of molecules, this is something that we can expect to see when we have femtosecond pulses. This is what Piotr is doing now, how molecules bend, how they oscillate, how protons is transferred from one position in a molecule to another. This is all femtosecond scale story. The next step towards attoseconds, we need energy, or we need power. So we take these pulses and we amplify them. And this is the story that you might have already heard. Actually, Kasia was, if you look at this notebook with that is circulating somewhere here, the very first colloquium was in 2018 about pulse amplification. So what do we do? If these pulses become too energetic, if we go from nanojoules to millijoules or even further, they will destroy any material, because the electric fields are so strong that they will destroy any medium. That's why we have to stretch them first, make them long, but of course in a controlled way, not in any way. Then we want to amplify, and since this is now a long pulse, typically on the order of hundreds of picoseconds up to maybe a few nanoseconds, the instantaneous power is still safe for the amplifier, and then we want to compress. And then this goes up to the roof, and then we can have a short pulse, typically maybe 20, 30 femtoseconds, because this stretching compression is not 100% reversible, so usually we will lose some phase relations, and maybe 1 millijoule or more. And all this is called chirped pulse amplification. And again, in my story, this is the next Nobel Prize from 2018 for Moreau and Strickland for generating high intensity. That's what we mean by high intensity short pulses. We will need to do one more step, because this is too long for us. If we want to explore attosecond world, this is too long for our technology of generating short pulses. So we will do spectral stretching, and this is done in a capillary filled with gas. And this is my prop I have here. This is a part of the attosecond, a real part of the attosecond laser setup, and that's where this capillary sits from here to here. These are ports to fill it with neon or argon and to control the pressure inside. And when these pulses propagate in this gas-filled capillary, they accumulate nonlinear phase because the intensity is now high enough, and we can broaden the spectrum and subsequently compress this again to get something like 5 femtoseconds and 1 millijoule. Well, there is loss, of course, so maybe from 1 millijoule we don't get 1 millijoule, but anyway, this is going to work that way. So ultimately what we get from here are ultra-broadband pulses, it's worth realizing that the spectrum of these pulses often spans from omega to 2 omega. So it's not a narrow-band source. It's definitely a very broadband source. We know how to amplify them and compress, so we can control the phase. What is also important, we know how to measure these pulses. And this is where our lab had some contributions several years ago with our colleagues from Oxford. We were working on a method called SPIDER. There are two methods, SPIDER and FROG. So you see these femtosecond people like fancy names. This is essentially spectral interferometry, and this is some kind of nonlinear gating. All these techniques are purely optical and based on some optical nonlinearities, electronic nonlinearities. This is also, I will refer to that later when we go to attosecond. One last thing that we want here is so-called carrier envelope phase stabilization, CEP. What does it mean? Such short pulses, if we plot the electric field, it will probably look like that in the infrared. But what about if we take this pulse? It has the same envelope, the same carrier frequency, but there is a shift here, and this is what is called a carrier envelope phase. And it turns out that for application in generating attosecond pulses, this is critical. And it's a non-trivial technical challenge how to stabilize this offset in a femtosecond amplifier. All right, we are almost there. So now we take these pulses. And well, now we have to work in vacuum because what we generate will be XUV. Is it W? No. Yes? Oh, okay, thank you. And we just have a stream of gas, can be argon or neon, and we send these pulses, which are short and have very high intensity, and we hit the atoms. And then what happens? So the first classical model that was developed and still commonly used is based on understanding an atom, or actually an electron, this is an electron in an atom, in a bound potential. And now it's good to realize what's the strength of the electric field that this electron feels. And well, it is on the order of 1 volt per nanometer, or maybe even 1 volt per angstrom. So that's a very high field. But our pulses can generate fields of comparable strength, which means this potential of an atom, when it sees the electric field of the pulse, will start to wobble like that every period of the electric field. So every 1.3 femtoseconds, if the pulse is at 800 nanometers, the potential will be disturbed by the external electric field of the pulse. And then what happens, now I need 3 hands. What happens is that the electron in this kind of tilted potential can tunnel from this bounding force, or from this binding well, can travel some distance from the atom, but then after 1 femtosecond, this starts to be like that. So it feels the force that pulls it back towards the atom, and then it kind of collides or recombines with the atom. So there are like 4 steps. It's actually called 3-step model. tunneling, ionization, travel far, go back, collide. And during this collision, this energy that the electron accumulated during this travel must be somehow dissipated. And it turns out it's emitted as a beam of XUV radiation of very interesting spectrum. Now I have examples of high power. So this is still here, what we can generate. We can actually go to terawatts now. And actually, if you compare this 1967, when they had microseconds and a fraction of gigawatt, it was at that time this was the power that Stockholm was using with all the factories and lights turned on. Now we have femtoseconds and terawatts, so this is approximately the installed power capacity of the whole world, which is estimated to be 8.5 terawatts. So this brings us here to this year's Nobel Prize, and this is also a side remark. People were able to generate attosecond, or let's say 1 femtosecond pulses with a different technology called cascaded Raman. So essentially there is one frequency and you don't need any femtosecond sources. That's very cheap, very convenient technology. You just take high power laser, you generate Stokes and anti-Stokes, and then if the intensity is high enough, these two can now generate their Stokes and anti-Stokes, and as a result, you get equally spaced frequencies, exactly what we need for short pulses. But that turned out to be a dead end. So it's good to realize that it's not always, you know, a straight word towards Nobel, but this never was developed further. And this is the first result from JFISB of this lady, now the Nobel laureate, where they observed the spectrum of these harmonics generated here. Why harmonics? Because it turns out that what we see here are odd multiples of the carrier frequency of this pulse. And maybe it's a good exercise for students to realize why we only see odd harmonics and not even harmonics. And what do they say? Well, it was surprising for them that the efficiency of this process was relatively high. Well, it's not really that high, but for them it was high enough to be surprised. That these harmonics are actually generated into a narrow cone. So it's not that they are generated everywhere, but rather it is a beam of light. And that the intensity of these harmonics is relatively constant. So you see this is the 9th harmonic, 11th, 13th, and so on. This is in wavelength, so they are not equally spaced, but they are equally spaced in frequency. And the intensity only changes by a factor of 2 or 3 or 5, maybe up to 21st. So that was a surprise as well. Why we have so many harmonics generated with relatively constant intensity? And they didn't think about attoseconds at that time. They just thought, well, it will be a good source for XUV spectroscopy. That's what they expected. But later, it turned out that not only these harmonics are generated in the stream of gas, so we actually have something like that, but also that their phases are coherent. Their phases are locked automatically. So, in fact, we can expect that they will make a short pulse. This is the 3-step model. This is the order of magnitude of the intensity and electric field that are involved here. And this is an even broader spectrum of harmonics, now spanning from 15th to, actually people have seen 300th harmonic. This is not very useful, but anyway, it can span further and further. The wavelengths typically here are on the order of tens of nanometers. So that's approximately 1/10 of a wavelength of visible light. And well, soon enough, they learned how to measure these pulses. I will talk about measuring in a moment. And they saw first bursts of pulses. So you see, of course, this potential wobbles all the time, and with every wobble, different atoms different atoms can have these electron round trips, and then every half cycle, a burst of light as an attosecond pulse will be generated. And then there was a big challenge was how to generate a single attosecond pulse, and that was done a bit later. And now we can have an isolated pulses. This is done in two ways. Either we can filter this spectrum, so we can choose only a certain bandwidth, or we can also control not only the electric field of these pulses interacting with the gas, but also their polarization. There is another degree of freedom. We can have a pulse that has, let's say, vertical polarization here, which turns horizontal somewhere in the middle, and then vertical again. And it turns out, since this process of interaction with atoms is very sensitive to polarization, clever shaping of the polarization of the pulse can lead to an isolated pulse. Here is some recent... that's what these are methods of generating isolated pulses. And here are some recent results. So there is 43 at plus minus 1 attosecond pulse generated a few years ago. I'm not sure if this is now the world record, probably not. One last remark is about measurements, so or metrology. How do we measure these pulses? And there are two techniques which are somehow corresponding to these two. The technique based on interference is called rabbit, and the one based on gating is called streaking. No fancy name here. And to be very brief, rabbit is used for measuring trains of pulses. So in the case we generate a train of attosecond pulses, we have them interact with gas as well, so another stream of gas. And then we measure this is actually, it says photon energy, but this is actually energy of the electrons emitted from this interaction, minus the ionization energy. And people realize that in this process, when we send attosecond pulse, so this one, and a small portion of that pulse, of that femtosecond pulse that was used to generate it, into another stream of gas, and we vary the delay between them. This is the horizontal scale here. So we change the delay between these two. We will see at the harmonic frequency, we will see a constant signal here. But between the two harmonics, we will see a signal that oscillates with delay. And these oscillations can be understood as, again, spectral interference of two paths leading to this frequency. So the atto photon can be absorbed and an infrared photon emitted, or the two can be absorbed. And from the shift in these fringes, which is very similar to that, we can calculate the phases of these individual harmonics. And once we know intensity and phase, we know everything. We can go to time domain and we know how long the pulse is. While streaking is a bit similar to this. Again, the setup is the same, but now we use a single attosecond pulse. And since this interaction strongly depends on the field of this femtosecond pulse, we can think about it as the electrons being emitted by the attosecond pulse in the presence of the electric field of the femtosecond pulse. And again, when we change the delay, we see this energy of emitted electron changes, and from this, by some iterative algorithms, if we understand the interaction process, we can tell how long the pulses are. Actually, both of them, both femtosecond and attosecond pulse, can be characterized from this data. It's a lot of data, by the way. Okay, thank you very much. That's about generation, and now Kasia will tell us something about what can be done once we have these pulses and we know how they look like.
Let's abstinate with the questions until the end of the colloquium.
Oh, okay. Good morning, everyone. Do you have this? Yeah, it's on mute, isn't it? Yeah. Good morning, everyone. So thank you so much for inviting me to tell you something about Nobel Prize in Physics that was. So, is it working or not? Is this better or not? Słychać? Okay. Okay, so generally speaking, the Nobel Prize is awarded for the greatest benefit to the mankind. So my purpose here is to show you that this is really the case. And all these three people, Pierre Agostini, Anne Lullier, and Ferenc Krauss, they do deserve the Nobel Prize. So Piotr very nicely covered the first part of the laudation that says that the award was given for experimental methods that generate attosecond pulses of light, and I will try to cover the second part where the emphasis is put on what you really can do with attosecond pulses. Before I go there, I would like just to supplement briefly to add one information to the story that Piotr told you, namely that in 1992 there was a paper published. It was a theoretical proposal of how to do train of attosecond pulses. So the first train of attosecond pulses was really generated on a piece of paper, and many people consider 1992 to be the year when the attosecond science was actually born. Later on, like 9 years later, Pierre Agostini did the train of attosecond pulses, generated a train of attosecond pulses in the lab, and only then Ferenc Krauss isolated one of those pulses. So with this, let me go to the applications. So first of all, for the first 15 years or so, attosecond pulses were basically used to do some basic research. We had to learn how to characterize them. We had to learn what sort of physics we can study having those pulses. And only very recently, there are some ideas of where we can take those pulses and where can we apply them so we can benefit from them more. A typical experiment which uses attosecond pulses is a pump-probe experiment. This is a rather simplified scheme of how the experiment really looks like. But basically, in the pump-probe experiment, what you are doing, you take the laser light and you divide it into two sub-beams. With one of them, you produce a pulse train or a a single attosecond pulse or a train of attosecond pulses, whereas with the other submeme that you can delay, you later on combine those two and you shine it on your target, which can be atoms, molecules, or solid system, and then you see what is happening in your experiment. So the first very important application, I would say, or achievement of attosecond physics was the direct measurement of how electric field of the laser light really is changing in time. So this is like a total inequality. We don't need to tell students anymore that through some evidence we can say that light is a wave. We can say that this was actually measured because we had this new tool that are attosecond pulses. So this is Piotr explained how attosecond streaking works, so I just want to finish at this. The other application, I would say, is that you can really look at the electron dynamics in matter, and this is very nice experiment which shows that. So I will try in a simplified words to describe it. So first what you do, you take the krypton atom and you shine the strong femtosecond pulse on it, laser pulse, such that you can singly ionize it. So you basically kick out the electron out of that atom. So what you end up with creating is basically a krypton ion. And then what is happening is that the electron that is in the valence shell of this krypton ion is really in the superposition of two states, and those, or manifold of states. And those manifolds, they have a small energy difference, very tiny energy difference, which, however, is very important because it defines you the relative phase between those two components of the superposition, which also defines how this electron wave packet is evolving in time. So now, once you have this electron wave packet that is oscillating in time, you are shining the attosecond pulse that is very weak. So what it does is only that it gently probes this electron wave packet. Then what you are doing the absorption measurement. So basically you are measuring the absorbance of this attosecond pulse. And what you can see is that the signal of it is, of course, it depends, of course, on your electron wave packet that you are probing. So basically, then what you are doing is you are doing this experiment many, many times at different time delays between the pulse that is called, in this case, the pump, this laser pulse, and also this attosecond pulse that is probing your ion. So you are ending up with getting a very nice spectrogram in your measurements. But the most important thing is that out of the spectrogram, you can see that the absorbance of the attosecond pulse is also oscillating. And basically, it follows the oscillations of your electron wave packet that you are really probing. So you can reconstruct very nicely the electron wave packet, and you can see how this is changing in time. The other experiment, which is also very nice, it's related to, it shows basically the electron charge migration. So this is already done with very complicated molecule, which is a kind of amino acid. And what you can see is when you shine the attosecond pulse on it, and then it follows it's followed by the femtosecond pulse, a weak one, and you do this experiment at different time delays between pump and the probe. You can see that there is some rearrangement of the electron cloud in your molecule, and this was actually what was seen in the experiment. There is some, they were able to see some oscillations in the signal of the yield of one of the fragments, which is being generated due to ionization by attosecond pulse, and they were able to figure out that this is somehow related to more or less how this electron cloud is migrating between the amine and the carboxylic groups of that compound. So this is like very already complicated thing, but the point is that you can, using attosecond pulses, you can really look at the dynamics of the electrons, whether those are simple atoms or very complicated biomolecules. This is the example, which is somewhat different. So basically, it shows that attosecond pulses can be used to look at the dynamics of already ionized electrons. This experiment was done in helium, and what you can do in helium is you can do ionization close to the resonance with an excited state, 2s to p state. And what may happen is that you can directly ionize with your attosecond pulse the helium atom, or what you can do is that you can excite the atom, and the point is that this 2s to p state has finite lifetime. It's not really bound state. So after some time, which is of the order of 16 femtoseconds, it basically breaks apart, and the electron also gets to the continuum, and those two pathways can interfere. So you can see interference in the spectrum of the attosecond pulse that is driving this process, and it shows a very unique, the absorbance of attosecond pulse shows a very unique shape, which is called Fano profile. So basically, this Fano profile is the signature of interference. And now the way you can look how this interference builds up is by killing it. So if you send the strong femtosecond pulse very quickly after the attosecond pulse, then what this pulse will do, basically, it will ionize this excited state, so there is no time for the interference to build up. So the shape of the absorbance line will be totally different than the Fano profile. So you repeat this again at different time delays between the attosecond and the femtosecond pulse. So you can really see how in time this interference builds up. As I said, this relates to the free electron already, and this is the experimental result that shows that. One of the topics that was actually addressed by attosecond physics was time delays in photoemission. I don't know whether this clock is working. Yeah? Okay. So photoemission is, of course, a very fundamental quantum mechanical process where you have the large energy electron that basically kicks out the electron from the target. And this experiment was done with neon atoms where they were ionizing neon with attosecond pulse and then used femtosecond pulse to do the streaking. And the question they posed was whether photoemission is really an instantaneous process. This was the question they asked. Or maybe we just simply didn't have the tools to see that otherwise, that it's not an instantaneous process. So with this experiment, they were able to measure that there is some time delay, whether the electrons are somehow ionized from the 2s or 2p shells. There is 20 attosecond delay. And the argument they gave is that photoemission is not really a single electron process. The electron is surrounded by other electrons, so there are strong correlations between electrons. So for this reason, there should be some time delay depending really on the, from which level you do ionization. This experiment was a little bit puzzling because for like 7 years people were not able to really explain this result theoretically. They were getting different time delay, so finally after just 7 years this experiment was repeated by other group with the rabbit technique that Piotr described, and it's amazing. This was the experiment that Anne Lullier did. So the amazing thing is that in that experiment they were able to achieve very high temporal as well as very high spectral resolution, and only because of that they were able to see that what the other group was measuring had some contribution from some other process that is called shake-up. And once you somehow disentangle the contribution of that process from what you are looking at, then the experimental results are really in a very good agreement with theory. So basically, this problem was kind of solved, but this is sort of, questions that you can ask when you have attosecond pulses to your disposal. So basically now I would like to say maybe about some experiments that were done for giving some prospects for possible applications, which is probably maybe even more important. And the first one concerns petahertz electronics. So basically, I'm not really a tech person, so maybe you know that even better than me, that there is some limitations on the current electronics because we cannot have better control on or faster electronic response with current technology that is based on semiconductors, because this movement of electrons is producing too much heat. And however, the wideband semiconductors react very quickly to optical fields. So the first experiment which were done with such wide bandgap semiconductors were done in silica. And what they did is they took a very short optical pulse, and strong enough such that they were able to bend the conduction and valence band. And basically what they were able to have is the tunneling of the electrons from the valence band to the conduction band. And using attosecond technology, they were able to measure that this process is very fast. It takes like a few hundreds of attoseconds. So this, of course, gives some hopes that we can have some optical-driven electronics working at bigger, based on semiconductors and working at higher frequencies than now. On top of that, in one of the experiments, they were able to see that this process is reversible. So it means that once those electrons are promoted to the conduction band, then after some time they basically relax to the valence band. And this is really like you know, the direction which is pushed by people doing attosecond physics, also including Ferenc Krauss, because attosecond pulses are used here for getting all the information we want or we need to get this work, you know, and be used. And the first actually demonstration using this wide semiconductors, the first demonstration that we can really get to petahertz frequencies with this wide bandgap semiconductors was done in gallium nitride a couple of years ago. So I know that many people from our faculty is somehow interested in this material. That's why I'm mentioning this. And final example, this is the paper that was published a couple of years ago from the Ferenc Krauss's group, where they showed a new technique of doing infrared spectroscopy. And this seems to be really important for medical applications, and this is also the direction which Ferenc Krauss is pushing. So this method, I have a movie which I downloaded from the web page. It goes like this. If you take a sample of molecules, let's say this is what they really demonstrated for, that this method works. You take the sample of molecules, you shine the infrared, very short pulse on it. So then this molecule will start vibrate in the presence of that pulse. And as the result, it will start to emit radiation at various frequencies, which are very characteristic for this particular molecule. And of course, all the sample will do the same. So what is coming is a very tiny signal which follows this infrared pulse. And then if you use attosecond pulses to characterize that signal, which they, by the way, called molecular fingerprint, then you can get the idea about what kind of molecules was in your sample. And this is exactly what they did. This was the proof of principle experiment where they used this organic molecule and they diluted those molecules in water, and then they demonstrated this infrared spectroscopy works surprisingly well. So in the next step, they basically took the blood samples and they analyzed them using this molecular fingerprinting technique. And it really works. You can really get a chemical composition of your blood sample, and for this reason they already did a couple of clinical studies for the cancer patients. And what they saw was that, first of all, with this method, which is based on very short, including attosecond pulses, what they can do is differentiate between healthy individuals and cancer patients. They can differentiate between different sorts of cancers, as well as they can even, and this was the most recent study probably, which was done for lung cancer patients, where they were able to differentiate between different stages of that cancer. So the point is here that using this technique, you can actually catch the disease before it really starts to, before it's too late, let's say. it this way. So the idea is to take, patients, people, and then do this molecular fingerprinting over the years and be able to take those blood samples, analyze them, and then, of course, there is the hope that this will allow us to actually catch the disease at the early stage, which, of course, is very important, especially for cancer. So this is actually what Ferenc Krauss is doing in Hungary. He's Hungarian origin, and he convinced Hungarian government to donate lots of money for this kind of the research. So this is really, I don't know maybe whether it's very hopeful or not, but this is the way that where attosecond physics can be, the field where attosecond physics can be really useful. Piotr asked me also to mention our links to this Nobel Prize, this year Nobel Prize. So one link is Maciej Lewenstein, who graduated from our department, but now, of course, he's a big boss somewhere else. But his papers that are the most cited papers, and he's the mostly well known for, those are the theory papers on high harmonic generation that he published with Anne Lullier. Last year there was Radek Łapkiewicz, who had some links to Anton Zeilinger, and this year we have two of our graduates, which are Paweł Wnuk and Maciej Kowalczyk, who work very closely with Ferenc Krauss, and specifically Maciej Kowalczyk is very hardly involved in this Laser for Life medical project that he is running now in Wrocław in collaboration with Ferenc Krauss. And this is the quote I would like to finish with, because I think this is very relevant to this year Nobel Prize in Physics. This is from Max Planck, who said, "The greater the detail in which we can pursue nature on any path, the richer and more durable will be the gain that we can derive from our perceptiveness." So with this, I would like to thank you.
Yes, we thank both speakers for their fascinating lectures. And now these talks are open for questions and comments. Rafał.
So I understand the benefits of these ultra-short pulses for studying the dynamics.
Yeah.
But you mentioned that it's generally useful for studying the composition of the molecule. So why there is an advantage? Because I could do it with shorter pulses and maybe get the same chemical composition of these molecules.
You cannot do infrared spectroscopy because for your sample you need it to be like typically how it's done. Those samples are diluted in water or something, and water absorbs infrared radiation. And so they are working on a new source of infrared, which is Maciej Kowalczyk that is doing in Wrocław. But actually you are right. The attosecond pulses here I used to basically analyze the spectrum.
But Rafał, composition is not interesting because in organic molecules there's always carbon, hydrogen, oxygen, sulfur, phosphor, and that's it. What is interesting, how these atoms are connected. And with looking at these oscillations, you can actually see the bonds. And this is interesting because from the bonds now you can...
So longer pulses would not excite these vibrations, you mean?
Essentially what they do here is doing Raman spectroscopy, but in the time domain. Normally when you do Raman, you excite an oscillation in I don't know, CH2 stretching, and then you look at the spectrum. Here they actually are able to see this CH2 stretching in real time. So I don't see that there is really much new information here, but it's a nice demonstration. Like with femtosecond, we were able to go from looking at molecular spectra from spectroscopic techniques, so from frequency domain to time domain. Now we can do the same, but with much faster oscillations.
Are there any other comments? Yes.
With attoseconds, we are now, in a sense, measuring the electrons moving within molecules. Is there any need to go further on? Because zeptoseconds, let's say.
Yeah, zeptosecond would be useful to...
For what?
To look for what? Proton movements in nuclei?
Nuclear dynamics.
Yeah, for
Nuclear
nuclei
dynamics. Yes,
yeah.
so that's completely
So
out of atomic thing, but
yeah,
we
this
are
is
going. Okay.
completely out of atomic field. And of course, all these methods based on high harmonic generation, they would rather not work.
Because the energy would be enormous with
you need enormous
zeptoseconds.
energy in order to really get to zeptosecond pulses, right? And for this, you really need relativistic physics.
Okay, yeah. So that would be nuclear thing and not atomic. So that's the end of atomic measurements, let's say.
Okay, you never say.
Yeah,
never.
But roughly.
But probably
more or less.
You are
more
right.
or less. Okay, thank you.
So sorry, one more question. So, and why particularly these gases, these noble gases you use for this generation? There is no helium, for example. Helium would not work? And why other gases? Why I cannot use just, I don't know, nitrogen or hydrogen? Why I need these particular gases? What's so special about them?
I mean, you can do high harmonic generation out of solid surfaces.
Yes,
it will work as well. So...
And you don't want molecules to...
Okay, but why not helium, for example?
I don't know.
But, I mean, there were experiments done in helium.
Okay, so it's not particular because you
the
wrote
first,
argon and neon, and I thought that maybe it's for some reason the only one.
The first experiments were done with rare gases, right? But you can do it for helium too. There were experiments done for helium.
So what these two give is a spectrum that looks nice, and by looking nice, I mean there is if you look at the whole spectrum, there is some region where, of course, the lower harmonics, if you look at the third, fifth, and so on, they are on this scale they are 10 to the power of 5, probably higher. But then when we started looking at, let's say, 11, 13, and so on, they have so-called plateau, so the intensity is more or less the same over a range of harmonics, and that's what people like, to have equal intensity more or less, because there is a hope that you cannot generate short pulses. You know, if this is completely random intensities, and you add them up, then probably no attoseconds.
But there is any physical feature of these atoms that make it happen, or?
As far as I understand, each gas has a different spectrum, and these give spectra that are most convenient to be added up to short pulses.
Just to answer Rafał, so helium has much lower polarizability and hyperpolarizability, which contributes here by orders of magnitude than, for example, xenon, which was used. So the effect would be much smaller for helium.
Yeah, that's what you need. The atom with, or whatever, the target with low polarizability. That's true. But it was demonstrated for helium as well. It's just not very good target.
And as a follow-up to the previous question of Rafał, and a question to Piotr, so in what way this medical in medical application, in what way it is better in comparison to what you do with Raman and things in the blood?
To be honest, I'm not very much convinced, and I am a bit surprised why these attosecond pulses are good enough for a Nobel Prize, because as far as I know, and maybe I'm wrong, but there were no really new insights into understanding nature, so no really new insights into physics. Of course, they demonstrated a lot of beautiful experiments that we can now study this dynamics of electrons, see the orbitals in real time, but we didn't gain really deep new insights into the structure of matter. Neither was there any plausible application path demonstrated. So, of course, the technology is beautiful. It's terribly complex and terribly difficult, but I would probably rather wait for a while so that it can demonstrate, apart from its beauty, also some significant contributions either to knowledge or to technology. But, well, maybe their thinking is different.
Turns out that I'm very close to microbiology now. So when you have the enzyme, for example, and it opens up for a really short time to open up some, I don't know, a pocket where some drug can enter, it's really, really short. So that's why I think in biological, not especially the composition of blood, but the very, very short biological thing that open up that are never seen, for example, in X-ray, because it is an excited state. So when you make an X-ray of a protein, it is never seen there. But for a very short time it opens up, and maybe it's useful to know the very, very short process in biological samples.
SAP.
I have a very theoretical question. So in your lecture, those pulses are completely classical creatures, but I guess that there is also some quantum structure behind. So is this? So I understand that we deal with some coherent states. So this is why they are so as classical as possible. But there are some limits. So do you see some quantum properties of those pulses as well?
Wow. Not really. I cannot think of, let's say, experiment that would show that. Oh. I mean, I cannot think of any experiment that would show that, basically. So, sorry. Which one?
There is experiment which measure the quantum effects in high harmonic generation, but the effects are very small.
So the model that I have presented is, of course, completely classical. And there was a quantum model, but as far as I know, there wasn't really much progress with this quantum model. It's not that we were able to see or understand something much better. So it seems that with high fields, quantum physics has not yet been explored properly.
Yes, thank you. Maybe I will have the last short question, because before the lecture, not after, there was a question of Krzysztof Kacpierz that I liked, and I let myself repeat it. What is, with such a spectrally broad pulses and short pulses, what is the wavelength and what is the uncertainty of this pulse position in spectral domain?
Of course, whenever we have short pulses, we have broad spectra. So when we start here at 800 nanometers, so the spectrum will typically be centered at 800 nanometers, but will span to generate 5 femtoseconds at 800, you need roughly 200 nanometers of spectrum. So this will be delta lambda. Here we are, let's say, this plateau that we use to generate pulses, this is centered, let's say, at 30 nanometers, and the width will be on the order of, I would say, between 5 to maybe 10 nanometers. So that's the order of magnitude. So you can say the spectral bandwidth is a fraction of a central wavelength, of the carrier wavelength.
A significant fraction. Thank you for coming today, and I thank both speakers for their lectures. And you are invited for 18th of December. Professor Tomasz Dietl will have a lecture on the possible future of physical units. Thank you for coming.